Related rates. A related rate situation is one in which more than one distance is varying. So in other words, it relates the relationships between different variables and the rate at which they are changing. Implicit differentiation is used because we're differentiating each term or each variable with respect to time t. So like optimization, on which I also have videos, such an explanation is much oversimplified, so examples are the best way to become familiar with this concept. The radius r and surface area s of a sphere are related by the equation s equals 4 pi r squared. Write an equation that relates ds dt to dr dt. So this is our equation for the surface area of a sphere. So simply by differentiating both variables, s and r, we can yield the result that relates ds dt to dr dt. So differentiating with respect to t, we get ds dt equals 4 pi, that's our constant, times 2 r dr dt. The radius r and surface area s of a sphere are related by the equation s equals 4 pi r squared. Write an equation that relates ds dt to dr dt. So before we start this example, I want to begin by an overview of differentiation in general, just to really understand the concept that we're going to do in this example more fully. So let's say y equals x. Let's differentiate. So the derivative of y is 1 with respect to y, dy. Derivative of y is 1 dy, which is equal to the derivative of x, 1 dx. Rearranging, we get dy dx equals 1. So going back to this example, derivative of s, we're going to differentiate this equation. So the derivative of s is 1 ds dt. We're relating this variable s with time, so the derivative of s is 1 ds with respect to time, so 1 ds dt equals 4 pi, which is a constant, the derivative of r squared, which is 2r, times dr dt. Because we differentiated r, indicated by the dr, with respect to time, over dt. So ds dt equals 8 pi r dr dt. As such, we've related ds dt to dr dt. The radius of a sphere increases at a constant rate of 2 inches per second. When the radius is 10 inches, at what rate is the volume of the sphere changing? Let's first draw a diagram. So we have our sphere. Know that this distance is our radius, r, and the formula we're going to use is volume of a sphere is equal to 4/3 pi r cubed. We know r is our radius, and we're also given another piece of data. R is equal to 10, but we're also given a rate. So the constant rate of 2 inches per second is what? It's the change of the radius of the sphere, with respect to time, because we're changing per second. So what does this mean? We have a change in radius divided by a change in time, because radius is measured in inches, divided by the time measured in seconds, so change in r over change in t, infinitely small changes in r is regarded as dr. Infinitely small changes in time, t, is dt. So dr dt is the derivative of r with respect to time. So instantaneous changes in r related to instantaneous changes in t. And what is this? This is 2, because this is our rate of change of the radius. So let's differentiate the volume formula with respect to time, so we can relate the change in volume of the sphere with the actual radius of the sphere. So dv dt is equal, we have our constant 4/3 pi, times the derivative of r cubed is 3r squared, times dr dt, the derivative of r with respect to t. So dv dt is equal to 4 pi r squared dr dt. We know dr dt is 2, so dv dt, change in volume with respect to time, is 4 pi r squared times 2. dv dt equals 8 pi r squared. At the instant we're concerned with, radius equals 10 inches, so dv dt is equal to 8 pi times 10, the radius squared. dv dt is 800 pi. And what are our units? Change in volume with respect to time, inches cubed per second.